Alright, let's talk about surface tension and viscosity. Surface tension is another physical property of a liquid in particular that can be explained by intermolecular forces. And once again, the greater the intermolecular force of the substance, in this case a liquid, the more energy you will need to put in to break it. Alright, so let's first explain what surface tension is. Simply put, when you have a liquid, if there is an object that is coming in contact with that liquid, some solid object, initially what happens is that the weight of the object creates a force of, you could even think of repulsion. This is kind of related to buoyancy and fluid mechanics, really. But you have a force acting upon your liquid, and this force is basically trying to break apart some of the interactions that the liquid-liquid molecules have. So the surface tension to some degree mitigates that because it's directly a representation of the molecules being attracted to each other, not wanting to depart from one another. Now, the greater the intermolecular forces of attraction are among the liquid molecules, the harder it is going to be for this object to break that interaction, and the more resistant the liquid is going to be to breaking its surface. So the resistance to break the liquid surface is really what we refer to as being the surface tension of the liquid. And looking back at the examples that I explained in the past, um, if you have any of these molecules in the liquid phase, by having the proper temperature, they will have some degree of surface tension, but it will increase as you do have greater intermolecular forces. So the same trend that we saw for the boiling point applies to surface tension as well. This molecule will have the lowest surface tension, followed by the molecule in red, which has greater surface tension, followed by the one with hydrogen bonding, which has even greater surface tension, and ending with the one with the ion dipole bonds, which or intermolecular interactions, which will have the greatest surface tension altogether. So there is actually, in that sense, no difference between boiling point and surface tension. The trend is exactly the same. So as long as you come up with a trend for the boiling point, that trend is going to be the same for the surface tension. And you've seen examples of this probably in the past, specifically when you have water on the paint on your car or some other um, hydrophobic paint. The water has a better interaction among itself than with the paint. And so what ends up happening is that you end up creating these spherically shaped droplets, and the same thing is shown here on this leaf. The water kind of creates this spherical shape because by doing that, it maximizes the number of interactions among the water molecules while minimizing the interactions with the other surface. And that's completely surface tension characteristic of water, which is a result of its high intermolecular force of attraction among molecules. The other trait that you may have witnessed is what you see right here on the final figure. You have a daddy long leg or a water bug basically walking on water, and the reason being is that as a result of the long legs, this insect is able to spread its weight over a great surface area. And by doing so, at any one given point of interaction with the water surface, the amount of force applied to the water is actually much lower than if this thing were to have only one leg. In that case, it would probably sink to the bottom, but and drown, right? Which will be not good news for it. But because it's spreading its weight, you can actually walk on the water because now the force that it's applying onto the water is not strong enough to break the hydrogen bonding intermolecular forces of attraction, and that's what allows this thing to walk on water, which is also incidentally the reason why they tell you, like, if you ever, and I don't recommend you doing this, but if you end up being stuck on a frozen lake, they tell you to basically lay flat on your stomach and move that way out of the lake because that will basically spread your weight and minimize the possibility of breaking the ice and basically sinking into the frozen lake. So it's kind of interesting interactions, really. All right, now the other one is viscosity. And viscosity is a trait of liquids in regards to how much they flow. Um, Depending upon what the intermolecular forces of interaction are, the stronger they get, the harder it's going to be for you to break the liquid into the droplets that you see here, not only flowing but also falling out of the container that we're in. And so viscosity simply measures in the tendency to flow of a liquid. What is that tendency? And as you might have guessed that, yes, the greater the intermolecular forces are, the harder it's going to be for you to break the liquids into these droplets or to allow the liquid to flow out. And so you're going to have what we call greater viscosity in your liquid. And a perfect example is shown here in this figure, where you have 5 test tubes angled at the same position, the same angle, and the substances in them are different, however. And what you can see is that depending on their intermolecular forces, some of them flow readily, like the one here on the left. Other ones flow a little bit less. You have less of a liquid stream coming out of it. Other ones barely make it out, and the last ones don't even come out of the tube. They're kind of like stuck there because their viscosities are greater, greater, and greater. And so this tendency to prevent liquid flow, which we call viscosity, can be determined and can be regarded in terms of the intermolecular forces. The greater they are, the greater your resistance to flow is going to be. And so, in other words, as you increase intermolecular forces, you do increase viscosity, the same way that you increase surface tension, the same way that you increase boiling point. So those 3 trends are exactly the same: viscosity, surface tension, and boiling point. And just to show you an example, right here we have a set of hydrocarbons, but hydrocarbons that contain carbon-hydrogen bonds, carbon-oxygen bonds, and oxygen-hydrogen bonds. And so all of these molecules here have only dispersion forces, dipole-dipole forces, but we also have hydrogen bonding. Except that as we go from left to right, there is greater amounts of hydrogen bonding present in the molecule. And also the molecules are getting bigger and bigger, so the molecular weights are getting bigger. So their overall interactions in terms of intermolecular forces are getting stronger and stronger and stronger. So the viscosity will actually increase going from left to right. And I couldn't help it. But yes, unlike what Pennywise would say, I would kind of rephrase his slogan and say, yes, you'll flow too, but only if the intermolecular forces of attraction say so, right? So sorry, Pennywise. All right, so let's stop the video right there, and on the next video we'll talk about volatility.